All right. So as far as we are concerned, I think we are ready for the next assignment, because last week, we kind of took a little break of no assignments. So the next one is called absolute value, and you can probably already guess what it does. Okay, we are going to write some code to take the absolute value of a register. So let me change it first so that it is now assigned, and that you guys can start to work on it in the lab. So the access code is ABS, and I'll make it do in a week. Today is the 29th of wrong year. Okay, so today is the 29th, so I'm gonna make this do in a week. But I do not encourage people to procrastinate, because this one, even though it is not very difficult as a homework assignment, um, it is still gonna take some time. Okay, and we'll assign it. Today is October 29th. There we go. And save and publish. So now we can see it. There we go. And I'll just go ahead and show you the preview of the homework assignment, just so that we know what the assignment is about. So I think this one only has got one question. Yeah, so that's only one question here. Maybe not, maybe a few. But the question is intended to help you understand, how absolute values work. So in the first question, the absolute value, usually denoted as bar x bar, the absolute value of x, can be computed using the following C function. So I know we haven't really talked about functions yet, how to call and how to return. So that's not the focus. The focus is really on the logic of absolute value. The rest of this lab activity is to write assembly code to accomplish this same computation. The first question is then how the processor can tell whether a signed integer is negative or not. As an 8-bit number, which bit must be a 1 if a binary number represents a negative value? So don't say out loud your answer, because that's supposed to be individual homework assignment. Okay, so if you are not sure about the answer of this particular question, you might want to read signed values. Okay, there's one module that talks about signed versus unsigned values. So that would be the module to read if you have that question. I believe the binary comparison module also has some information that can be useful. The second question is, how do we check the sign bit of a number? So, and you notice that I use sign bit and not the bit number, so that one question does not answer the other question. There are many ways to do it, but I want to use the least expensive method. This generally means avoiding the use of instructions that have immediate operands. Okay, so go ahead and think about how to do it. And right here, it basically says the last question, the actual question, is to get to the instruction we need to use. We first need to examine the ALU itself. Which flag in the ALU reflects the sign bit of the result of a computation, regardless of what computation it has just performed, with the exception of the instructions dec and inc. So decrement and increment do not affect the flags. So you have to choose from one of the below. Okay. So if you have questions, or if you have problem answering the previous question, the best way is to open up Logisim, go into the ALU module, and examine flags out as a port, and then trace your way back and find out which of those bits reflects the sign of a result. Okay. There are only 5 of them. Okay, so it shouldn't take too long to track down all 5. Number 3, now we are shifting our attention to some other instructions. Certain combinations of operations do not do much with certain combinations of operands do not do much with certain instructions. For example, AND AA does not do anything really useful. And the same thing applies to OR AA, because if you do OR a particular register with itself, it ends up with itself. Okay, it doesn't really do anything. This is why opcodes of some combination of opcodes is quote-unquote hijacked to do something else. So hijack means a binary opcode, a bunch of zeros and ones, that specifies a particularly useless operation is repurposed to do something different. Okay. Note that the assembler is rather dumb and cannot understand opcode hijacking. This means it is possible for two instruction mnemonics to assemble to the same binary opcode, so you have to be careful with that. So tag remembers the opcode of either the AND XX or XX family are hijacked for other instructions. Analyze the opcode table and find out which family is actually hijacked. So what it means is you have to go to the instruction table and use the opcode, the binary opcodes family for AND and also OR to find out, oh, is this opcode also hijacked for something else? Okay. Let me show you what I mean by that. Okay. So just go to the shared drive. The documents are all there. And with this one, the opcode table document should be able to answer that question. But I'm going to give you some pointers as to what to look for. And then we go to, okay, this is already in processors. This is opcode table as a document. And then the first thing you need to do is to look up at the AND, also the OR instructions. All right, so here's AND, this is AND, and this is OR. So with these two, you notice that the most significant 4 bits is 1100 for AND, 1101 for OR, okay? Now, what I said is, AND AA doesn't really do anything useful, OR AA also doesn't do anything useful. So in the case of AND AA, you have to think about what would become XX and what would become YY. Now you have to think about that code and go like, well, are there any other instructions here that make use of the same most significant 4 bits, but it does not have a mnemonic of AND or OR? So that's kind of what you're looking for, okay? And one of them is hijacked, the other one is not. So you have to figure out which one is hijacked and which one is not hijacked. Do we have any questions about what the lab is asking? Nope. Okay, very good. Moving on to number 4. So in question number 4, combining the results of the previous 2 steps, now we have an efficient way to check if the sign bit of a register is set or cleared. Let's call the mnemonic of the instruction that is not hijacked test XX, which it is not called test XX. It updates the sign flag according to the bit pattern of register X. Now, obviously, this is also helping to answer a previous question. I'm not going to say which one, but it is already answering one of the previous questions. Note that the mnemonic test does not exist, so do not try to find it in the opcodes table. It is just a placeholder here so that the question of one step does not answer the other question. This means the following sequence of mnemonics can be used to make a decision based on whether a register has a negative value when interpreted signed. So the first instruction is the non-hijacked instruction. In other words, test is either AND or OR, okay? I cannot remember which one, and right now I really cannot remember which one. So I'm not actually kidding that I cannot remember which one. So it's one of those two. So after you specify this instruction, obviously X has to be a particular register. Then you can use JSI to have a conditional branch to label L1 if and only if the sign flag of register X is set. So that's the idea, okay? So there's no need to compare, okay? You just have to use one single instruction and it can set the sign flag like that. So at this point, you may want to write some code, assemble it, and test it in the simulator to make sure this sequence of mnemonics does work as expected. Okay? So this is only a suggestion. There's nothing to turn in, but it will be helpful to do it. You can also inject a value in the register bank so that they're not all starting with zeros. So now the next question is, how do we perform arithmetic negation? Specifically, what is the name of the following value with respect to the bit pattern X? Okay, this is not negative. This is a tilde symbol. So tilde symbol means bitwise not. So we are taking the bitwise not of a bit pattern and then we add 1 to it. And it has a particular name. You want to find that name and click the correct answer. This was talked about when we talked about what are signed values. Okay, what is signed representation. So each lab is really a mini quiz, but with no time limit, so that you can review previous material. So in the next exam 2, you won't be, surprised when this stuff comes up. Okay, so now you need to look into the instruction set of text toy processor and figure out how to perform tilde x plus 1, okay? The negation of bitwise not of 1 plus 1, and x is a register. You may assume we want to perform the operation in place, which means we want to change the register in place without using any additional registers, for that operation. Once you're done with that, the program should stop at a halt instruction. Your code may contain multiple halt instructions at this point. Assuming the register that contains the value to find the absolute value is in register A, use the following space to copy and paste your program, the source but not the opcodes. So I want the mnemonics, not the hexadecimal code. Your code should not include any initialization of register A because I can inject values into it. And text version of this code has 7 lines including label definitions and all the instruction mnemonics. So it's just telling you that you can shrink your program to 7 lines. It doesn't mean that it has to use exactly 7 lines. So if your solution uses 8, 9 lines, it's fine. Okay, it's not a problem. But if you have time and you want to take on the challenge, you can try to see if you can specify the logic in the most concise way so that the entire program can shrink to only 7 lines of code. Is that okay? And that's it. That's the entire homework assignment. So the only thing to turn in is what you need to paste here into, so paste your code, your mnemonics into here. Do we have any questions about what this lab is about and how to start doing it? No questions? Yep. Mm-hmm. Uh-huh. Yeah. It's same as what? It's bitwise not. That is correct. It's a bitwise not operator. Mm-hmm. Any other questions? No other questions? All right. So if there are no other questions, I'm going to move on to the next module. I believe in the previous class we already talked about how to quote-unquote compile a C program into assembly code, step by step, 1 layer at a time. And let me just kind of go back to the section that we talked about last time. So last time we talked about this particular module, which talks about conditional statement. How do we flatten a conditional statement so it has no structure anymore? How do we flatten a while loop? And also how do we flatten a do while loop? So we talked about the flattening of control structures. And I believe we also talked about how to flatten expressions. So if there's a negation, how do we get rid of the negation? If there's an or, how do we get rid of the or? If there's an and, how do we get rid of the and? Is that correct? Okay, let's take a quick look, okay, so that you guys can tell me whether it looks familiar. So what I'm talking about, I'm 100% sure that we talked about the control structure, so I'm just not sure whether we talked about this. I believe we did. Yeah. Okay, yep, okay, very good. So that means this module is pretty much done. And did I give you an example, like how to do it step by step? No? Okay, all right. So what we'll do is we can take one of the examples. So this one is, this is a long example, but it is a complete one. So one thing you can do is to read this section of the document. It's really long, okay? So if you read this part here, you can see it's really, really, really long. But each time, I only change the program a little bit, okay? So you want to look at the delta or the difference between each version of the code to figure out, how I changed the program. So that's kind of, important because, this really shows, step by step how we quote unquote compile a program by breaking down C code into assembly code. Is that okay? Now, am I going to talk about this? Well, it depends on how. I mean, I can read it to you, but that's going to be a little bit boring. So I'm kind of relying on you guys to read the notes, prior to the class, so that you have some idea of how to do something. And if you're in your reading, you have questions like, I'm not really quite sure how these two steps connect, then we can talk about that in class. But because otherwise, this is really just an example of how to apply the techniques. Is that okay or not? Okay. So I'm going to let you guys, do some reading, and you can also watch the other class, lecture too. But there will be examples of, me actually showing this kind of approach to you. Well, let me see. I'll just do one example in today's class. Okay. It's not very long. Not nearly as complicated as this one here, but it will serve as an example. So I'm going to do it here. And since I can type a whole lot faster than I can write on the tablet, I'm going to use Notepad here, or mousepad. So what we want to do is to look at this code. Okay, if x is great, well, we'll make it 3 variables. If w is greater than x, greater than or equal to x, okay, and we'll throw in some logical operators, just to make it a little bit more interesting. And w is greater than or equal to y. This is pseudocode. Well, we can use C code if you want. There we go. So now it's actually C code. And we also want to use regular registers. So we have A, B, and then A, C here. Okay. Now, if A is greater than or equal to B and A is greater than or equal to C, amongst these 3 registers, we have just confirmed that A is the maximum. Okay, so we're going to use D to store the maximum of the 3 registers, so D equals A in this case. In the else branch, we know A is not the maximum, which means it is between B and C. So now we only have to compare whether B is greater than C. If that is the case, then B is the maximum, otherwise C is the maximum. So we are only looking at a fairly simple, logic flow of how to find the maximum of 3 variables, and then make the 4th variable the maximum. So is that okay so far? Okay. So this one is kind of helpful because it demonstrates, how do we deal with the flattening of a nested structure. It also demonstrates how do we flatten a conjunction. Okay. So what do we do when we have operators inside the condition? Okay. So we'll start with this, and what is going to happen is there will be a lot of copying and pasting. So the first thing we do is to flatten it until we cannot flatten anymore in C code. So we flatten this part first. So we basically look for the negation of this condition as a reason to go to the else portion. So we say go to the label else, and then we get rid of the structure. In other words, we get rid of all the curly braces, because the use of curly braces imply there is structure to the program. And then over here, we use an unconditional goto to end if. And then else, instead of a keyword, now it becomes a label. I believe this program cannot compile anymore because I don't think you can use a reserved word like else to serve as an identifier of a label. So if you want this program to compile, you probably have to change else to else 1, else 2, or something like that. So it's not just else itself. Uppercase else would work too, because keywords are case sensitive. And then we also get rid of the curly braces down here, because we're removing all those labels. Removing that structure. And then the label end if is going to end up here. Do we have any questions about this transformation? Okay, we're just flattening the conditional statement 1 level. Did we talk about how to do this? Yes. If you do not remember, you might want to read the module, which is, I think it's the first part of the module that talks about the conditional statement. Okay, but we're not done yet, because from line 21 to line 28, we have another conditional statement that we need to flatten. Well, how do we flatten that one? Same way that we flattened the first one, okay? But you just have to be careful with the names of the labels, okay? So what we do now is we take this, Control C, and then just paste here, and then I'm going to change the inner structure this time. So once again, we negate the condition. Now right now I'm not doing any simplification because I'm just blindly doing the mechanical translation. So if the negation of the condition is true, we go to the else label, but this time I'll call it else else because it is the else inside the else. Okay, so now this label is now else else, okay, with a colon. And at this point, we can remove all the curly braces again because the structure of the inner conditional statement is now gone. Of course, so we also have to go to the end if label, but this is the end if label inside the else, so I'm going to use a prefix of else underscore so that we can differentiate between the two. Now the end if of this particular conditional statement is here, so we say else end if and define that label over here. And if you want this program to look as close as possible, you need a semicolon here. But that's really just syntax and not that important. There we go. So now the entire program is flattened as far as control structure is concerned. Okay, we don't see any curly braces anymore. We're not relying on the structure of blocks anymore. We do not rely on a statement containing another statement anymore. The only time you see a statement containing another statement is very, very mechanical. It is always a conditional statement containing a goto as its only then statement and nothing else. So at this point, the control structure is fully flattened. It's time to move on to the conditions. So when we come to the conditions, we have this one to flatten first. But when you look at this one, you can go through the mechanical translation process, which will work, but it is also very inefficient. So what we would also do in this case is to apply De Morgan's law. Have I talked about De Morgan's law in this class? Yeah. Okay. So, but that's okay. If you don't remember, I will talk about it just one more time. So De Morgan's law basically says if you have a negation of x and y, then it's really the same thing as saying the negation of x or the negation of y. I use extra parentheses to emphasize the application of the negation, but there's also the other half of this. The negation of x or y is also the same thing as the negation of x and the negation of y. So De Morgan's law applies to these two particular transformation rules. You can kind of look at it as the distribution of negation, because you can see how the negation was on the outside before, now it's on the inside. But unlike a normal distribution where you do not change the operator, this one does change and to or, and then or to and. Okay, so that's called De Morgan's law. Now De Morgan's law in this case is really quite helpful because we have one case like this where we have a negation applied to the result of a conjunction. So that means we can apply De Morgan's law. All right, so let's go ahead and simplify this code this time using De Morgan's law. So we, once again, copy and paste this code. And then this time we look at this and go like, we know how to use apply De Morgan's law. So we change the negation and we apply it to the inside. Okay, like so. And then we have to change the conjunction to a disjunction like that. Is that okay? All right, so we look at this and go like, can we optimize this even further? In other words, can I simplify and get rid of the negation without costing us, an additional goto and an additional label? So we look at this thing here and go like, can we specify this comparison in a simpler way so that the negation is out? Well, since a is an integer, b is an integer, a is greater than or equal to b, or the negation of that is a is less than b. Okay? So we look at this and go like, yep, we can definitely simplify this. This becomes a is less than b. And what about this one? Well, same thing. So we look at this and go like, it's just A is less than C. So at this point, I can't really do a whole lot of simplification any further. So my attention is now going to this one here. Now with this one, I can change the original code a little bit and say it is if B is greater than or equal to C, because when B and C are exactly the same, then both are the maximum. So it doesn't really matter which branch we go to. So that would make the simplification easier, but I'm not going to go back and change it just because it's easier at this point. So I'm going to stick with whatever is here. All right. So at this point, I got a few choices to go. I can either flatten the or I can deal with the not here. Okay. I'm going to go work with the or first. So we look at this, Control C, Control V, and we go like, I think there's one particular rule that says if you have an or, you can look for one condition at a time and go to the label that we're supposed to go to. So that means, the easiest way to do that is to copy and paste the original and only get rid of 1/2 of the expressions. Okay, like so. Get rid of that. And we can get rid of some extra parentheses at the same time. And the bottom one is kind of the same thing, except we keep the second one and get rid of the first one. Okay, like so. Have we talked about this? Turning a disjunction into getting rid of a disjunction. We have talked about it. Okay, so if this looks new to you, that means it's time to review the notes. All right, so with this gone, we can now work with this guy. So with this guy, we can say, well, we can do it like this. Get rid of the not, turn it into less than or equal to. Is that making any sense? Okay. So now we look at this and go like, it looks like we can't really simplify this any further. So it's time to convert it into assembly code. Now, up to this point, okay, up to this very point, if you change the word else or the label name of else to else1 or something like that, so that it's not the reserved word, the program will still compile, which means we can still test the program as a C program using C or C++ code blocks and stuff like that. And you can catch any error in the conversion process with a high-level programming language environment, which is great because at this point you don't have to use TTP at all. There's no assembly code whatsoever all the way up to this point. Okay? So when it's time to convert into assembly code, we just have to convert this into assembly code like one step at a time. I'm just double checking what I had earlier. There we go. So now what we do is we take all of this and then we do the conversion basically one line at a time. So Control C and then the Control V. There we go. All right, so we do it one line at a time. So we comment out this one, because in assembly code you can actually comment out using //. So now we look at this and go like, how do we do this? Looks like it involves a comparison between A and B, and we only branch to the label else if and only if A is less than B. So now it is important to know, but are these registers signed or unsigned? Because whether A, B, C are signed or unsigned will now determine should we use the carry flag, which is also known as the borrow flag, as an indication whether one is less than the other one, or should we use the L flag, which is used for signed interpretations of whether the minuend is less than the subtrahend. So now we have to kind of really make that decision. So unless I tell you whether A, B, and C are signed or not, there's really no way for you to choose the right mnemonic at this point. So I have to tell you. So let's say they're signed, okay? So we have signed int A, B, C, and D, okay? So this extra information is now really important. So now we can say CMPAB. The compare instruction itself doesn't really care whether they are signed or not, because whether you are subtracting a unsigned integer from another unsigned integer, or whether you're subtracting a signed integer from another signed integer, it's still the same subtractor. The same thing goes for addition. So that's why the compare instruction is insensitive to whether you're dealing with signed versus unsigned values. But the next instruction is going to be sensitive. So we have to use j blah l, j blah I, to the label else. In other words, we are jumping to the label else if and only if this particular flag is set. So in the case of signed comparison, it's the L flag that matters. The L flag is the exclusive OR between the sign and the overflow flag. Where do you find that? In the module that talks about comparison, binary comparison, but it can also be found in the processor itself inside the ALU expressed as gate logic. Okay? So that's where you can find the definition of all of these things. So this is using the JLI instruction. So that part is done. And so this one is also really easy to deal with because instead of comparing A to B, I'm comparing A to C. So CMP AC, JLI also to else. Okay? What about this one? What about copying D to A? I mean, excuse me, the other way around. Copying register A to D. What instructions should I use here? There's a CPR instruction or copy register. So if you look up the documentation, let me go to the assem opcode table. And CPR is right here. So if you look at the CPR copy register instruction, that's all it does. Okay, it takes the second operand and copy it over the first operand, which is exactly what we need to do in this particular program. Okay, so we just go back to our code here and say this is CPRDA. I intentionally preserve the meaning of left-hand side versus right-hand side. So that means, when you have D equals A, it translates directly to CPRDA because D is the destination and A is the source. So that makes the translation process a little bit easier because it is consistent with the assignment statement of C, assignment operator of C. All right, so we're almost done with this part here. Go to. What instruction should I use instead of the go to statement? Is an unconditional branch, JMPI, okay? So don't forget the I because otherwise it has a slightly different meaning, okay? The definition of the else label is the same whether we are doing C or not, okay? So we can now move on to the next one. So this one, once again, is going to boil down to some kind of compare followed by some conditional branches. So we look at this and go like, okay, we have to first compare B and C. But you have to look at this one, a little bit. I kind of short-circuited the whole thing because B is less than or equal to C is not exactly one single comparison. It is really translated into B is less than C or B equals to C. Does that make sense? Okay, it's just that the shorthand is B is less than or equal to C. So that means I'm checking for both. I'm checking for less than, let's go. I'm checking for equal, let's go. Okay? Less than we already know because we can just say JLI to else. Okay? That's for less than. But equal to is actually pretty easy too. So does anyone want to take a guess of which flag? The zero flag, exactly. The zero flag indicates whether A, B, and C are the same in this case, because when B minus C is 0, it means B and C have to be exactly the same. Okay, so that's why the Z flag, which is set if and only if the result of an operation is 0. So that's why if the Z flag is set, it basically tells us that B and C are exactly the same. Yep. Yes, but I'm doing a fairly syntactical translation. It is not the case that B is greater than C. So this is a JZI, okay, the checks for equality. So now we can move on to the next line. We know how to do this because it's just copying one register to another register. So this becomes a CPRDB. We have a go-to, which becomes JMPI. And you can kind of see how I am keeping the indentation of the original code, because just in case I need to come back and fix the code, knowing the nesting of the assembly code in correspondence to the original code does help. Okay, else can stay the same, and now we just have to translate assignment here to CPR DC this time, and another label definition, we're done. All right, so this is kind of the gradual process of converting from C code into assembly code. Now in this class, I'm not going to give you guys code that is just for the sake of doing stuff, just kind of, how should I put it, tedious, okay? So I'm not going to give you, some business logic code that is like 20 lines long in C, but it's really just the same thing over and over again, okay? So when you have the next test or your homework assignment, it's going to be something that is just testing whether you understand how to convert it or not, okay? But I might give you combinations like a while loop. Inside the while loop is a conditional statement or something like that. But the process doesn't really change, okay? You just have to do the flattening one level at a time. And as long as you name the labels in a very structured way, they're not going to collide, okay? So you won't have any big problem with that. So we okay so far with the conversion process? Actually we just compiled a C program into assembly code. That's basically the process. So are we good so far? Okay. So if there are no questions about this, then we're going to move on in the notes. So once again, there is some extra material in my notes here. So you might want to kind of just at least kind of glance through the example that I have shown here. So this is a simple example, but you want to go through the longer example just to make sure that you kind of understand the process and understand what is the transition between the versions of the code. Okay, so that might be helpful. But other than that, we're going to move on to the next module now. The next module is calling and returning from subroutines. This is a fun one. Okay. All right. So now that I show you, where the note is, okay, it's relatively short even. Okay. So now the question is, how do we do this? There's calling and there's also returning. Is it still working? Where's the returning? Oh, okay, so here's the call and that's the return. Okay, I just didn't make a new section heading for that. All right, so the first thing that we need to talk about when we talk about calling and returning is the concept of last in, first out. Okay, otherwise known as a stack or LIFO. Does anyone have any exposure to the whole concept of last in, first out? Okay. In real life, we have a lot of examples of last in, first out, and many of those is not actually what we want. Okay, so when you're packing a U-Haul truck, okay, assuming it's a normal U-Haul truck, the first thing that they put into the U-Haul truck is going to be the very last thing that you retrieve. That last bicycle that you push in, before you slam the tailgate, it's going to be the first thing that falls off the truck when you open the tailgate. That's last in, first out. A refrigerator, unless you are very self-disciplined, is also last in, first out. Okay, that orange juice that you look and go like, I don't think I want to drink that. It's still at the back of the refrigerator. The color is slowly turning from orange to purple. But unless you're disciplined and go like, oh, I need to throw that stuff away, it will still be in the back. At the same time, what you just bought from Safeway is going to be right at the front of the refrigerator. Okay, so once again, it's last in, first out, except in this case, we really don't want it to be last in, first out. It just kind of works out that way. In order for a refrigerator to be truly not last in, first out, two doors may help, and having a carousel in the inside that rotates may help as well. So here's your $1 million idea that you can sell to GE or some other refrigerator manufacturer and go like, hey, if you do it this way, people will really like it because now they can actually get to the food that they have put into the fridge for the longest and use it first. Okay, but that's the concept of last in, first out. But in computer programming, last in first out is known as stack operation, or the stack abstract data type implements last in first out. So the first thing I want to do is to show you this example here, because when you look at the flow of this particular example, I mean, I'm assuming you guys know what this is going to do. Okay, this program doesn't do anything useful, but what it will do is it's going to call f, which means execution will continue from main to f. That's the first call. So the first question that you need to kind of think about is, how does it know where to go back to in main? When f is done, f doesn't do a single thing, but when it's done, how does it know how to get back to main so that it can call the second f? Okay, and the second f is going to do the same thing. It's going to continue execution in f, and then when f is done, it will go back to main. But this time it go back to the return statement, because otherwise it will just be calling f by itself all over again. So now the question is, how does it know? That's the biggest question. How does it know? So what do you think? What is the mechanism that allows it to know, oh, I need to go back to main there when I'm done? There has to be some kind of cooperation between the caller, main in this case, and the callee, which is f in this case. So what is happening? Okay, so if you read out the text here, it basically says the location of where to go back to in main has to be stored somewhere in memory. Okay, and this is also kind of important because this is also the basis of recursion. Recursion is a little bit worse in the sense of what it looks like, but in terms of the actual mechanism, recursion is no different from a normal call. So what we'll do is we'll kind of take a quick digression to talk about what a stack is, what kind of operation we can expect to perform on the stack, and then we come back and answer the question that I have highlighted on the whiteboard, on the projector. Section 3 talks about a stack, what a stack is. So I'm going to skip all of this stuff here and skip all the way to just the C code, because it really boils down to the C code. So the C code says your stack size is 32. This is a macro definition. Some of you may not be familiar with a macro definition. You can kind of look at this as const int stack size equals 32. Okay, kind of have the same meaning. Not exactly the same, but for what we are dealing with here, you can consider those to be the same. So, and then the next line, uint 8 underscore t stack in square bracket stack size is really just declaring an array of 32 unsigned 8-bit integers. And the name of the array is stack, S-T-A-C-K. The third line is declaring a pointer called SP, because it's short for stack pointer, and it's a pointer to a uint 8 underscore t, because ultimately we want that to point to a location on the stack. Are we doing okay so far with those 3 lines of C code? Okay, that's okay? All right. So in the description here, we said, assume the stack is from location 255, which is the very last location in RAM, to the last byte available after the program takes, the space that is taken up by the program. Okay, because the program always starts from location 0. That's how the assembler works. Okay, the assembler makes the assumption that you want the program to start from location 0, and it counts down. Okay, well, I should say count up, so that the next one is at location 1, location 2, and so on. So your program is going to take up a certain amount of RAM. The stack can take up the rest, basically. So to make this happen, so that we can basically have a predictable beginning of a stack, this is important. The stack grows down instead of up. In other words, when the stack is empty, the stack pointer points to a higher location. When you start to use the stack pointer goes lower and lower and lower. As opposed to the more intuitive way of usually starting at the beginning, which means it's a lower memory location, and as we use more location, the stack pointer goes up. That's the more intuitive way, but the stack is always growing downward. Okay, you always point to the very last location, and then you go backwards. Another way to look at this is to look at your notebook. Okay, it's basically just saying that you're using the last quote unquote last page first. Okay, and then you move your way to the quote unquote cover, the front cover of your notebook. All right, so knowing that, the operation to store something on the stack looks like this. So we have, let me show the type declaration at the same time. So this way we can correlate, what is the stack and what is the stack pointer. So when you look at these two lines of code, sp minus minus is really the same thing as sp equals sp minus 1. Okay, all it does is to decrement the stack pointer. By doing that, I'm reserving space on stack. Because remember, anything below what the stack pointer is pointing to right now is available. Anything that is pointed to by the stack pointer and above is not available. Okay? So by decrementing the stack pointer, I'm reserving one more space, okay, one more byte. And then what I do is I'm just going to store whatever I want to store at that location. So this is also known as a push operation. It stores a particular thing onto the stack. Is that okay so far? Okay. So if we're going to store something on the stack, you probably would expect that maybe at some point we want to retrieve that from the stack. Okay. So how do we retrieve something from the stack? Exactly the opposite. When I say exactly the opposite, I mean opposite in every single way. So you can see how the last thing becomes the first thing to do. And then the assignment just flips the direction. In other words, we take a look at whatever the stack pointer is currently pointing to. We retrieve whatever is pointing to into X. Okay, X is typically a register. And then we say, oh, that location is not useful anymore because we have just retrieved the value of that location. So by means of incrementing the stack pointer, we are actually deallocating the stack by one location. We are making one more location available on the stack. Are we doing okay so far with these concepts? Kinda, okay. So that means, if you look at memory, should I use a tablet? Yeah, probably. I want to use a tablet because pictures sometimes can be useful, and I want it to be recorded. This is 310 Monday, Wednesday. Okay. All right. So what that means is if high memory. Oh, okay. Kind of switch this one too. All right. So that means if this is high memory is going this way, and low memory is low addresses are going that way. The stack, okay, is initialized at a very high location. In fact, when we initialize the stack pointer, it has to be 1 byte past the end of the allocated stack. Because what the stack pointer is pointing to is the last byte that we push on the stack. So when the stack is empty, well, if the stack is empty, what are we supposed to point to? Well, we just point to the one location that is just 1 byte past the end of the allocated space for the stack. Okay. As we push items, the stack pointer is going to go this way. It's going to decrease because every time we want to put something onto the stack, the first thing we do is to decrement the stack pointer, and then we store something to the location that it points to. When we want to push or store another thing, we do the same thing. We decrement the stack pointer first, so it points to the next available location, and then we put something there. Is that okay? What do we do when we retrieve items? We take whatever the stack pointer is pointing to, retrieve that, and then we move the stack pointer back up to the previous location, which is 1 byte higher than what it is pointing to. So that's how we use a stack. So this part has to do with how do we initialize the stack pointer. It becomes the stack plus stack size, which is the address of the 1 byte location that is past the last byte of the stack. That's okay, because we are never going to store information right at that location. Because the first thing we do when we want to store is a decrement first, which means it decrements down to the actual last byte of the stack before we store. So it's perfectly okay to initialize the stack pointer to be 1 byte past the end. Is that part okay? All right. Okay. So now we go back and talk about how do we call and how do we return. So when we call, this is what happens when we call f. Okay. In other words, this code here is implementing this in the main program, and also the next line with a minor change to the label. So we'll take a look at the sequence of instructions here and try to figure out what it is doing. It's commented, so you can actually read the comments and find out what it's doing. So the first thing is, well, there's no such thing as a dedicated stack pointer with TTP, text toy processor. Most modern processors do not have a dedicated stack pointer anymore, so the stack pointer is just one of the registers. So for the rest of this lecture, for the rest of not just this lecture, but of this class, we are assuming that register D is what we choose as our stack pointer. So register D, for the most part, is not available to do anything else because now it is the stack pointer. So the first thing we do is decrement the register D, which is the same thing as SP minus minus. It's equivalent to SP minus minus. And then in this case, I load L1 as a label. I load the value of label L1 to register C. Do we have to use register C? Nah, we can use register A, B, or C in this case. It's just one of the other registers. Anything other than D is fine. Then we store C to whatever D is pointing to. Do you guys still vaguely remember the ST instruction? I sure hope so. It's one of the first 3 instructions that we start when we first started to talk about the mnemonics of the processor. Okay? But the effect is whatever register C has, which is the value of label L1, is now stored in the stack. Okay? Whatever the stack pointer is pointing to. And then we do a JMP-I to F, which means we are no longer continuing executing in main, and then we go to the label F, which is indicating the beginning of the subroutine F. So that's the call, okay? And then L1 is actually defined here. Well, that's kind of interesting, because what we're doing is we're defining a label that is marking the 1 location right after the JMP-IF instruction. And then we are storing L1 on the stack. So effectively, that's all we're doing. We're taking the address of the byte that is right after the JMP-IF instruction, and then we put it on the stack. That's all we're doing. But by doing that, I am remembering where the subroutine should go back to. Is that okay? Because label L1 is where the subroutine is supposed to go back to. So now we look at the return instruction. Okay, how do we return from a call? So the return, which is going to be the last piece of code in F, is going to perform these 3 operations. The first thing it does is to go to the stack pointer and say, hey, stack pointer, what are you pointing to? Okay, I got this byte here. Okay, put it into register A. That's what the LD instruction does. LD and ST are basically opposite to each other. The ST instruction stores a register to a location pointed to by a register. LD is going to do the opposite. It copies the location pointed to by a register to a register. Okay? And then what we do is we increment D, because that location is not useful anymore. I have just retrieved the content of that location on the stack, so it's not useful anymore. So I increment the stack pointer to deallocate that location. Remember, the stack grows down, okay? The higher the stack pointer, the less content is actually stored on the stack. Since I've just used it, I'm freeing it, I'm deallocating it. The last instruction is one that we haven't really talked about, JMPA. JMPA has a very interesting description in the opcodes table tab. So since the opcode table tab is right here, we'll take a quick look at it. So we look at JMP and then X. I'm just trying to find it. Okay. There's a whole family of those instructions like JL, JO without the I, but JMP is right here. Okay. So the JMPX instruction or mnemonic has a very simple description. PC equals X. What does that mean? It means you take one of the 4 registers, A, B, C, or D, and overwrite the program counter with it. That's it. That's all it does. Okay? But what is the effect of this instruction? It changes where you're going to execute it, where you're going to get the next opcode. So whatever this register, okay, whether it's A, B, C, or D, is pointing to, that's where you're going. Okay? So if register, let's say it's JMPA, okay, and A has 26 as base 10 number, okay? That means after this jump instruction, the next fetch cycle is going to location 26 to fetch the next opcode. Because the program counter is really just that. The program counter is a register to help us keep track of where do I go to get the next opcode. So by changing the program counter directly to whatever a particular register is, you are redirecting the flow of the program to whatever that register has as a value. So are we doing okay so far with this instruction? Okay. So getting back to the module. Now this looks all kind of confusing in some way, I suppose. But how do you get to understand this code? That's the question. How do you start to understand this code other than trying to read it and understand from the text? What do you do to gain a better understanding of the whole concept of calling, returning, and using the stack to store the return address? Sorry? Plug in some code, exactly. So I'm giving you snippets of code here. It's not entirely complete, but we can just go ahead and do it. Okay. So let's go ahead and write some code and plug it in and see what happens. All right. I'm going to close off some tabs here because they are not needed. So all the LibreOffice can go. And nope, don't need to save. There we go. And then we go back to my text editor here. All right. So just for clarification purposes, I'm going to use main as a label, but it's actually not needed, okay? And then the first thing we need to do is to initialize the stack pointer. Now the last location of the stack is location 255 or FF in hexadecimal. What is the address of 1 byte past that location? That is still 8-bit long. What is 1 plus 1111 1111? It's all zeros. Thank you. Very good. So that's what we're going to initialize the stack pointer to. So the stack pointer is initialized to 0 because that is the one location that is 1 byte past location 255. Okay? There are 2 ways to do it. You can do the most obvious one, which is just putting a 0 into register D. That works. Or you can do the subtract D from D here. Okay? It does exactly the same thing. Because if you subtract register D from register D, what is going to be end up in D? A 0. Okay, so this instruction is actually shorter because it's a 1 byte instruction. There's no immediate operand to this. LDI D0 actually is a 1 byte longer. So if you're counting bytes, this is actually shorter, even though it is a little bit less obvious of what it does. Okay. So this is for initializing. So we are initializing the stack pointer at this point. So stack pointer is just register D. Okay. And what I want to do is to implement the code that is at the very beginning of this entire module. Okay, so once we have initialized the stack pointer, now we can go ahead and perform the first call. There are basically two steps to a call. The first one is to find out where we're supposed to go back to and push it on the stack. Then we transfer control to the subroutine. So what we need to do now is kind of do what we saw a little bit earlier. Register A is fine. I can use register A for this purpose. And we'll just say it is in the subroutine main. This is return location 1. And then we'll push it on the stack, which means we have to decrement the stack pointer. Okay, so this is allocating a byte from the stack. And then we do a st instruction. So we are now store return address main return 1 on stack. And now we are ready to perform the unconditional branch to wherever we are supposed to go. In assembly language programming, the name of a subroutine is a label that marks the beginning of the subroutine. So the subroutine F is nothing more than really just a label of the first instruction corresponding to the subroutine. So when you want to transfer control from a subroutine to another subroutine, the last thing to do is to do a jump. And then main underscore return 1 is going to be here, because that is a return address. That is where we want to come back to when the first invocation of F is completed. Are we doing okay so far? Okay. And then what do we do? Well, do the whole thing again. LDIA, but this time it is main return address 2. Decrement D again, STDA, and then JMPI to F again, and the main return 2 is here. This is how each invocation of F knows where to go back to. Because otherwise you can say, well, we can just put a JMPI instruction at the end of the subroutine F, then it knows where to go back to. Well, sort of. But if you did that, then it will always go back to the very same location. It's not going to say, well, I'm going to readjust where I'm supposed to go back to based on where I came from. They wouldn't have that ability. But doing it this way means that, oh, you just have to store on the stack where it's supposed to go back to, and then the subroutine can pick it up and go like, oh, I see, this time I have to go back to that location because it's now dynamic. The return location is now dynamic. So when we get back to main, we really don't have anything else to do, so we can just put a halt instruction here. So now here comes the fun part, which is the subroutine F. Now, if you want to convince yourself that F actually has something to do, you can always just put in some no-op instruction to say that this is the body of the subroutine, okay, which is empty. That's an empty subroutine. It doesn't really do anything. Now we can return, okay. But how do we return? Exactly the opposite of how you get to the subroutine, okay. So what we need to do now is to first retrieve what is on the stack, which is the return address. So we do a LDIAD, okay. So we now retrieve return address. I cannot say whether it's return address 1 or return address 2, because from the subroutine's perspective, all it's doing is to go to the location pointed to by the stack pointer and say, okay, that's going to be my return address. Grab that, okay? But I cannot tell whether it's return address 1 or return address 2. A subroutine doesn't know where the caller is, okay? All it knows is what location contains on the stack contains the address to go back to. But once I have retrieved that, I need to increment the stack pointer. That is going to deallocate a byte on the stack, okay? Then I can make use of it. To make use of it, I'm just doing a JMPA, which is copying the content of register A to the program counter, okay? And therefore, I'm continuing execution at whatever label that I used earlier to push that thing on the stack. Are we doing okay so far with this code? Okay, well, the program is all spelled out, what do I do next in order to gain a better understanding of all of this stuff here? Well, let's assemble and put it into the simulator. So we take up to here, Control C, go to the assembler, and go to the source tab. And just remove a bunch of stuff that I don't need anymore. And delete all that. Oh, it's view only. That's because it doesn't know that I have signed in. Alright, so refresh. There we go. Okay, that's better. And then paste. There we go. We got the whole program pasted. And then we switch to the RAM file tab. Do a file download as. And we'll call this call return.csv. And then we switch back to the processor, which I haven't started yet. Okay, so we'll start it here. And load it into RAM. Like so. Uh-oh. Oh, wrong image. So we need to go to /temp/call return.csv. All right, so now we got the whole program loaded. If I just do a Control K so that the clock takes as fast as it possibly can, is that going to help me? No, it would just kind of zip through everything and stop at the halt instruction. That's the only thing I can confirm visually is, oh, okay, it stopped at the halt instruction. So what do I need to do to understand this program or how it operates? I think tracing can help here. Okay, so we'll go to simulate and then go to logging. And there are a few things we definitely want to log. The program counter is definitely important, and we want it to be in base 16. The stack pointer is going to be important. So we go to the register bank and we pick out register D, and we also want it to be in base 16. What else do you think is important? What about the content on the stack? Well, after all, the content of the stack is what is storing the return address. I think that might be useful. Okay, so we'll go ahead and track those things down. So you basically have to go to the RAM component, and this part can be a little bit tedious because it shows you all 256 locations. I don't really need to track all 256 locations. All I really need to do is to track the last few locations. Okay, so we'll start with location 255, and then location 254, and maybe even location 253. The last two, I should never touch. But I just put it here just in case, okay? Just so that I know, I can confirm that those locations were not touched. All right. All right. If you want to throw in register A, that's fine too, because register A is the only other register that we used in this particular program. So we can throw that in and use base 16 too. There we go. And I'm just going to move it up so it is right, make it right below the program counter. There we go. So now we got most of the registers and RAM locations that we want to track, and it's time to actually run the program. Okay. And I will store into a file, and we'll put it into call return.tsv. That's going to be the file that we save it to. And that's all we need to do to set up the trace. Now we can type Control K to execute the program at full speed. Control K, and it's all done. Okay, we can confirm that it's all done because the program counter is not moving anymore, and the microcode pointer is not moving either. So now we are good. All right, Control K, and now it's time to take a look at that particular TSV file. I'm not going to use Google spreadsheet because it's really inefficient. So what I'm going to do now is to use my LibreOffice Calc, which turns out to be a lot more efficient compared to Google spreadsheet. So this is called return.tsv. CSV is the opcodes. TSV is the trace. And it can do all the conversion for us. It automatically detects it's a tab separated kind of file, and quoted field as text, detect special numbers. We don't want that. We don't want to convert into numbers at all. Okay, and we just click OK, and here is it still doesn't look very good. I'm just gonna abbreviate this to register A, abbreviate this one to register PC, and this is location 255, this is location 254, and this one is location 253. So this way we can shrink how much space it takes to display, to show all of the content. So we'll just do a shrink like that. Okay. Interesting. Okay. All right. Oh, this is not the program counter. This is register D. Oh, right. Okay, thank you. Which is also a stack pointer, so let's call it a stack pointer instead. And we'll shrink this one too. There we go. All right, and there's one more trick about using spreadsheets. You can use this thing so that the heading of each column stays in view as we scroll the rest. So that makes it easier to keep track of stuff. All right. So you can see that register A, got changed a few times, and right here it changed to 7. What do you think 7 is corresponding to? What was the first thing in main that put something into register A? It's an LDI instruction. Return, main return 1. Okay, so we now go back to the assembler, go to the assemble tab. And we just want to confirm that. Okay, all we want to do is to confirm that main return 1 has an address of 7. Yep. Okay. So that's why in the spreadsheet it showed that register A is now 7. And then the next transition is right here. What got changed here? The stack pointer got changed. And how was it changed? It's decremented by 1, so it decremented from 0 to FF in hexadecimal. Okay, very good. And then the next significant change is here. What is significant about this row? Yep, exactly. So that's a good observation. The stack pointer is serving as a pointer, pointing to location 255, and that is now storing whatever register A had. So the ST instruction is executed at this point. Okay. What does it tell you about the location of the ST instruction? The program counter is 5, and we can see the effect of the stored instruction. But where do you think is the actual location of the stored instruction? Remember, the decode cycle of an instruction increments the stack pointer. So by the time you see the effect of an instruction, the opcode or the program counter is already pointing past the opcode. So that means location 4 should be the address of the stored instruction. Okay? So let's go back and check with the assembler and say, where's my store instruction? Well, the store instruction indeed is at location 4. So those are minor little things that is really helpful to know, because by the time you need to debug your own program, knowing all of these little things can help speed up the process of debugging a program. All right, so what else is significant here? So we can see how the program counter is going like 1, 2, 3, 4, 5, 6. Whoa, what happened here? It just went to E, skipping all the things in between. Now we know the program counter can potentially skip one location because some opcodes take 2 bytes. Like LDI takes 2 bytes. The conditional branches like JXI, also take 2 bytes. So we can kind of see that sometimes it can skip 1 byte from the perspective of only tracking the program counter. But this is not 1 byte. This is like a big chunk. Where do you think location E is? Why is it low? Why is that location significant? That's the entry point of subroutine F. Exactly. That's where label F is defined. That's a very strong suspicion, but is that really the case? We need to check. This is the label F, and label F is at location 14 or E in hexadecimal. Okay? So we go back here and go like, oh, okay, that makes sense now. Location E is, in fact, the entry point of the subroutine. Okay? After we get into the subroutine, you can see the program counter just go like 0E, 0F, and then 10. Those are the 3 no-op instructions. Okay, so we know there are 3 instructions that really don't do anything really useful. And then we start to see some changes. So we start to see some changes right here. So what is the change here? What is the observable change of this line, of this row versus the one previous? The stack pointer went from FF to 0. That's the increment of the stack pointer. But wait, TAC, I thought we had an LD instruction right before we increment the stack pointer. But we are not seeing any changes. There's no visible change. Well, we don't have any visible change because we are copying 7, which is a location 255, over register A, which already has 7 as content. That's why it wasn't visible. Okay? But it is actually happening right there. All right, so what else is interesting? Ooh, what about here? So when you look at this particular row, row 19, what is the significance of row 19? Yep, the program counter changed directly from 14 to 7. What was significant about 7 again? We just looked into it. Yep, that's main underscore return 1, which is the place that we need to go back to when the subroutine is done. So returning from F the first time is successful. We can see from the trace on row 19 that we actually returned to the caller, which is main, at the right location. Are we okay so far? Okay. The rest of the trace is really the second call, which is kind of the same thing, except it went to a different location. So the location to go back to when you track this down is 0D. You can see how 0D is put into register A, push on the stack, and then utilized at this point to go back to the caller. Okay? So that concludes today's lecture, on how call and return is done. Okay? It is through the stack. And the stack is no more than just a chunk of memory in RAM that we use register D to point to. Okay? So please read ahead of me, because after this module, it will start to talk about other things about subroutines that are actually very useful. Okay, so we are going to head out to the lab and we can start on the homework assignment. I think some of you can get it done today, but there's no pressure to get it done today. You have until next Monday to get it done.